Hello Internet, welcome to the Empirical Sword, where science plus gaming equals awesome. I'm Lore Master DLC79, and today I want to talk about immortality. Yes, that's right. We read about them in books, in television. We don't read television, we see them in television, and movies, and myths, and legend, and folklore, and other forms of media that I probably don't know about. You know, the beings that could potentially live forever. You know, but what does the law? What does the law of physics say about this? And for those of you who can see through this veil of theatricality, yes, I am talking about perpetual motion machines. And we've probably heard at some point in our lives, possibly multiple times, if you study the sciences, that the laws of thermodynamics prohibit the existence of perpetual motion machines, which would technically also prohibit the existence of immortality. But why? Well, okay. Rather than taking you through all four laws of thermodynamics, I'll just focus on the two that are most relevant to the whole perpetual motion machine thing. So the first law basically equates heat to a change in an object's internal potential energy. You know, if we imagine an object as a collection of particles that are all moving around and bouncing off one another, this is all kinetic energy, but it's stored inside the object. It's not kinetic energy in the sense of, you know, a ball flying through the air, because all the tiny little balls are confined in an object, and they're not really doing anything out here. So it's potential energy. But if we bring this object in contact with another object, so that all these tiny little balls here are connecting with tiny little balls over here, then we can have energy transfer from one to the other. We can transfer that potential energy from one object to another, and this is heat. So officially, or mathematically, the first law defines a change in an object's internal energy state, its potential energy state, to the sum of its work output and its heat output. And yes, this can actually go in reverse. We could have heat input and work input that would increase an object's potential energy. And this is great, because now we've equated heat to energy, and we have the conservation of energy, you know, a law that is theoretically never broken. So, okay, let's for example take a steel block and get it really, really hot, and then put it inside of water, which is not really, really hot. Okay, so you know, the steel block is inside of water, and that heat is moving out into the water. The steel block is decreasing in temperature, and the water is increasing in temperature. And once they reach the same temperature, it stops. Okay, that's great, because I mean we've decreased the potential energy of the steel block, and we've increased the potential energy of the water. But based on the conservation of energy in the first law, we should somehow be able to scoop up all that energy we put into the water and then put it back into the steel block, right? Well, this is what physicists back in the heyday of thermodynamics research were kind of running into. It's not that easy. So they're missing something, right? You know, so what else is going on? Well, this is when they kind of came up with the second law of thermodynamics. And this, by the way, is going to be the meat of the entire video. The second law, one of its formal statements is that heat naturally or spontaneously flows from a high temperature to a low temperature, which is fairly common sense. But you know, just the phrasing itself, the spontaneous flow of energy from high to low, kind of implies that going from low to high is not that easy. So now, this gets a little difficult to visualize in words alone. So why don't we pop over to the virtual whiteboard and look at some diagrams. Okay, let's start simple. Let's say we have a simple boiler and a simple steam engine. And over the boiler, we are boiling water by burning a fuel source and turning the water into steam here at the boiler, which we are then conducting down this conduit to the steam engine, which does something. We don't care what. So applying the first law, what we have is some kind of fuel source that has some kind of stored energy, which we're then liberating by burning it, which produces fire, which then conducts that energy into the water, thus raising its potential energy. So much so that it boils, which, and producing steam, which then holds that excess energy that we've put into the water. And then we're conducting that steam and its stored energy down to the steam engine, which uses that stored energy to do something. We don't care what. So, okay, that's the first law. We're basically increase the potential energy of the water and then, conducting that energy down to a steam engine. So where does the second law come in? Well, let's zoom in on the conduit. So in the conduit we have steam, which is, let's say, 150 degrees Celsius, which is above the boiling point of water, which is what we'd expect for steam. Well, if we've just turned on our boiler, then our conduit casing is at room temperature, which is variable depending on where in the world your room is situated and what season it is, what time of day it is, and whether or not you have air conditioning. But by definition, room temperature is 20 degrees Celsius. And look here, we have a difference in temperature, or a temperature differential. And heat spontaneously moves down a temperature gradient. So we have heat moving from the steam, and remember, heat is energy. So we have energy moving from the steam into the conduit casing. And if you remember another video some time ago that I did, in which I introduced an equation, delta Q equals mc delta T. Well, the conduit casing, it has mass, that's M. It has a specific heat, that's C. And we're adding Q to it, thus we're increasing its temperature. And if we assume that our steam engine is doing its thing in the air, then we have to take into account the air temperature, which is probably going to be the same as our room temperature, which is 20 degrees Celsius. And we've just increased ever so slightly the temperature of our conduit casing, which means we have another temperature gradient. So heat moves from the conduit casing into the air. So that means that as we're conducting steam down the conduit, we're also heating up the conduit casing, which is then adding that heat, which is energy, into the air. Thus, as we're conducting our steam, which is carrying our energy, heat, to the steam engine, it's leaking out through the conduit casing. Why is this? Okay, so let's simplify this even further and consider just two generic arbitrary objects. A red object composed of these red particles over here, and a blue object composed of these blue particles over here. So if you look at the red object composed of these red particles, all these red particles are moving around with some amount of mass and some amount of momentum, and they're colliding with one another. Well, mass and momentum, that equals energy, kinetic energy, right? And when they collide, they transfer kinetic energy from one to another. But the total amount of kinetic energy contained in this red object remains the same no matter how many times or how energy gets transferred from one red particle to another red particle, because all that energy is still contained in that entire collective of red particles. So now this is sort of an internal energy, which we are kind of relating to heat, because remember, heat is a change in internal energy. And of course we can say all this about the blue particles over here. But this collective of blue particles don't necessarily need to have the same internal energy as the red collective of particles, right? So now if this is somehow related to heat, what's temperature? Well, basically temperature is how frequently these particles are colliding with one another and approximately how much energy on average is being transferred from one to the other, which technically we can't measure unless we're transferring energy to the object or from the object, because that's how thermometers work. But that's a little complicated, so let's not worry about that. The point is, the frequency of collisions in this red particle collective is not going to be the same as the frequency of collisions in this blue particle collective. And the average energy transferred from red to red is not going to be the same average amount of energy transferred from blue to blue. So they're going to have different temperatures. So if you bring them into something called thermodynamic contact, which we will simplify by assuming it's physical contact, so that red particles can collide with blue particles. Well, what's going to happen? If a red particle collides with a blue particle, and if we assume that the red particle has more energy than a blue particle, then when a red and a blue collide, then there's going to be, more often than not, there's going to be a transfer of energy from red to blue, meaning that blue will increase in energy and red will decrease in energy. Which means that we've taken energy from the red collective and transferred it over to the blue collective. And if this happens over time, then this is what happens. We just transfer heat from red to blue, or from high temperature to low temperature. Which means if we go back to our previous slide where we have this leaky conduit that is leaking energy out into the world, sure, we can wrap it with insulation, but that insulation is still made of particles. Like these particles here. And, of course, our insulation is going to be at a lower temperature than our conduit casing. And, of course, if we wrap another layer of insulation around that, that's going to be at an even lower temperature, and so on and so on and so on. Which means that at any layer of interface, such as between the conduit casing, which is hot, like these red particles, and the most internal layer of insulation, which is going to be less hot, like these blue particles, we're going to wind up with a transfer of energy from one set of particles to the next. And it's going to be the same for the next layer out, and the next layer out, and the next layer out. So we can wrap our conduit casing in as much insulation as we can find in the entire world, and it's still going to be leaky to some extent or another. We can slow down the leakiness, but we can't bring it down to zero. Okay, so we have an understanding of the first law, and we have an understanding of the second law, but what does all this have to do with immortals? Well, let's assume we have an immortal machine, which I will call the iMachine for short. And let's say that our iMachine is living in some pool of a finite amount of fuel. A very large amount of fuel, but it's still finite. And yes, I realize the fuel on the upper right is out of alignment, but I don't care. So, anyways, fuel and the iMachine. Let's say that the fuel is some sort of, let's say, chemical compound that has some type of internal energy. And the iMachine can internalize the fuel and somehow tap that internal energy, bringing the fuel down to some lower energy state. Well, first law, no, conservation of energy. That energy has to go somewhere. Into the iMachine, of course. This is why the iMachine is taking in the fuel. It needs the energy to do something. But this is a transfer of energy. So it's going to be leaky, because it's subject to the second law. So, okay, we have all this fuel, and the iMachine is going to be taking in this fuel because it needs E amount of energy to stay alive for some time. Now, staying alive, physically that is defined as work. And some time, well, that could be seconds, minutes, eons, millennia. Choose a measurement of time, and that's what some time is. So anyway, it needs E amount of energy to stay alive. But remember, the transfer of E from the fuel to the iMachine is leaky, which means it actually needs to take in an amount of fuel that is equivalent to E plus Q1, because that Q1 is going to be wasted. The E is going to be transferred into work or staying alive, whereas Q1, that just leaks out as heat. Now, let's keep in mind that E plus Q1 is a finite amount of fuel. And the iMachine lives in a finite supply of fuel. So if every time some time passes, the iMachine consumes E plus Q1 amount of fuel, eventually after some number of some times, it's not going to have enough fuel to keep going. So even though the iMachine has some kind of mechanical structures inside of it that will allow it to keep staying alive or doing work for an infinite amount of time, when it runs out of fuel, it can't do that. But what if we get sneaky? What if we invent these things called recycling machines, or R machines for short? Because, after all, conservation of energy. E is neither created nor destroyed. It is just converted into some other form. And Q, that is neither created nor destroyed. It is just converted into another form. So E and Q1 are still out there somewhere. So if we can invent some R machines to tap E and tap Q1, and then funnel that energy into reconstituting the fuel, then we could theoretically and definitely resupply the fuel, so that even though the I machine has a finite amount of fuel available, we could just recycle it indefinitely. So it's like it has infinite amount of fuel, but except when we take E and Q1 and put them back into the fuel, that's a transfer of energy. So it's leaky. So the truth is, the amount of fuel, the amount of energy that gets put back into the fuel is equal to E plus Q1 minus Q2. So let's compare this and this. The amount of energy that we can put back into the fuel is Q2 less than the amount that we started with, which means that we can recycle all of this energy as much as we want. Every single step, and in other words, every single some time, we're going to be losing Q2. So this looks like sad news for Immortals. It's like, even if they have the potential to live forever, eventually they'll just run out of energy, and then they can't do their living anymore. But this is only assuming a finite amount of starting energy, right? What if we assume that the universe has infinite energy? Well, we kind of run into an issue there, because to get an infinite amount of energy in a universe that looks anything like the one we live in, we would need infinite space, because infinite energy inside finite space equals black hole, and we probably don't live in a black hole. Let's assume we don't live in a black hole. So, okay, infinite space with infinite energy. That can actually happen, because we don't know if space is infinite or finite, because light travels at a finite speed, which means that we can only see out a finite distance. Beyond that, we don't know. It's question mark. Okay, so infinite space, infinite energy, right? So now our immortal machine, or our immortal, just like here, can take in their local energy, process it, and have whatever waste products build up, and, well, they'll diffuse out, and new energy will diffuse in, right? If we get the numbers just right, our immortal machine could potentially run perpetually, based on a constant influx of infinite energy and a constant diffusion of its waste products away from it. Except the second law rears its ugly head in a very sneaky way. So sneaky, in fact, that I don't think I can actually cover it in this video. I'll probably have to do another video just on this one little aspect. But it has to do with the internal structure of our immortal machine. If we assume a machine kind of machine that has like struts and gears and other things, you know, each individual component is composed of particles, and they're kind of jiggling around, moving around, and kind of disorganizing. They're kind of reshaping themselves, and some bits are kind of flying off into space. In other words, even structure itself is breaking down over time. And yes, it takes a very long amount of time, but if we're talking immortals, they have a long amount of time. And an immortal will kind of need to keep its structure for an infinite amount of time. So, yeah, again, I'll have to do another video on this. But there's even more. Cosmic expansion. Space itself is expanding and kind of pushing everything away. So that kind of means that energy is somewhat diluting itself. And eventually, things will get so far away from each other that not even light will be able to travel between them, because the space between them will be expanding faster than the speed of light. And if you want to know more about this, check out PBS Spacetime. They do such a wonderful job talking about cosmology. But speaking of cosmology, dark energy. This cosmic expansion is being fueled by dark energy, but dark energy is constantly being produced. It's violating the law of conservation of energy, which implies that our law of conservation of energy doesn't actually exist, at least not on a fundamental level. Okay, at some distant part in the future, our infinite amount of energy is being pushed away from our immortal machine so fast that it can't reach our immortal machine. But dark energy is constantly being produced. So we can constantly produce energy? So this raises a lot of question marks. Question marks that I'll leave to you down in the comments. That was the chair. That was also the chair. Constantly kind of jiggling around. That's the word, that's the word, that's the word. And I forgot to stop recording. If you like this video, then why not hit that like button? In fact, even if you didn't like this video, why not hit the like button anyway? Just to be nice, you can call it your good deed for the day. But if you really did like this video and you want to see more like it, then why not hit the subscribe button? Then my videos will just show up in your subscription feed. And you know what? If you have any kind of feedback at all, leave a comment. If you thought I did something wrong, or you've got something wrong and you want to let me know in a constructive, positive manner, then leave a comment. If you thought I did something really right and you want to congratulate me, leave a comment. If you have suggestions for future content, leave a comment. In fact, if you just have a simple question like what I had for breakfast, leave a comment. I can't promise that I'll answer all of them, but I will definitely try to read all of them. So until the next video, goodbye.